Hello, I'm Seema and welcome to part 23 of the chapter Organic Chemistry, Some Basic Principles and Techniques. We have been doing the fundamental concepts in organic reaction mechanism in the past few videos. In this video, I'm going to do two small subtopics. Although I have covered this portion in the parts before this, yet it is important to explain this properly now. The first subtopic that we will be doing is electron movement in organic reaction. How do we show the movement of electrons when we are writing down the reaction mechanism? And the second is the electron displacement effects on covalent bonds. This is basically just an introduction to the remaining portions that we would be doing in subsequent videos. But right now, let us just kind of revise this once more. Electron movement in organic reaction. I told you when an organic reaction in an organic reaction mechanism or in any chemical reaction, previous bonds break and new bonds are formed. So there is a movement of electrons which causes this change in bonding. The breaking of bonds is separation of electrons. The formation of bonds is coming together of electrons. So when previous bonds break and new bonds are formed, in other words, what we are talking of is just the movement of electrons. So how do we represent these electrons in chemical reactions? When electrons move in a covalent reaction, usually they do so in two ways. One is where an electron pair moves together. It may result in the formation of an ion, which may be an intermediate. But an electron pair moves together. That means two electrons move together. These two electrons could move from one bond to another, to an adjacent bond. They could move from an atom to an adjacent bond, or from a bond to an adjacent atom, which I'll just explain. But in all of these, the electrons are moving together as a pair. And the other possibility is that there is an electron pair which is moving, that is electrons from a bond or a lone pair, but they move separately. They do not move together to the same position. That is, the starting point and the finishing point are not the same. They may end up at they may start from the same place, but they end up at different places. So there we say that a single electron, we are showing the movement of a single electron, or we are showing the movement of a pair of electrons. When you show the movement of a pair of electrons, we use a curved arrow. A curved arrow, and we call it the curved arrow notation. So what do we do in a curved arrow notation? A curved arrow shows the movement of two electrons, that is one pair of electrons, from one position to the other. So curved arrow notation shows an electron pair movement in an organic reaction. And in other words, what is the movement of a pair of electrons? A pair of electrons forms a bond. So it is showing you the change in the bonds. How the bond is changing from one place to the other. Now the different ways how this movement may occur, but in each case you will be using a curved arrow, the curved arrow notation to show it. So take a look at this first example. Here there's a double bond, and then there's an atom Y, and there's a single bond. And the curved arrow has been shown from the double bond to the single bond. What does this show? This shows that two electrons from the second bond, they have moved towards this bond, or this bond now turns into a single bond, because what is a bond? A bond is a pair of electrons. So if it has a double bond, it means it has two pairs of electrons. If one pair moves to the adjacent bond, now this bond has only two electrons, that is one pair, so it is left with a single bond, and this bond which already had two electrons now gets two more. In other words, it becomes a double bond. The four electrons will form a double bond. So the bond shifted from this direction to the other direction. From one bond to from one side, the bond has moved to the other side. So how do we what do we call this? That the movement of electrons is taking place from a pi bond. The second bond is a pi bond. The first bond is a sigma bond, if you remember. So from the pi bond to an adjacent bond. The pi bond moves from one position to the adjacent bond, means the next bond. So we see two electrons moved from here and went to the atom Y on the other side. So joining whatever atom is present here, it would go and form a double bond with that atom. So that is, and it is shown by a curved arrow notation, and the curved arrow has this complete head, and that shows 2 electrons. The next possibility how a curved arrow can show the movement of a pair of electrons, the first was from one pi bond to an adjacent bond. The second situation may be where there's a pi bond and the 2 electrons are moving from the pi bond, but they're not going to the adjacent bond, they are coming to the atom. So the 2 electrons, they break the bond and they come towards this atom, thereby this atom gets a lone pair of electrons. So the bond that was a double bond now, the pi bond, it moves and it gives a lone pair on Y. So on both sides you are left with only the sigma bonds. So what is the movement, electron movement here? It has moved, it is a pair of electrons because it's a complete curved arrow. Therefore it is a pair of electrons which moved from a pi bond to an adjacent atom. It did not move to the adjacent bond, it moved to the adjacent atom. And the third possibility is that this lone pair of electrons on any atom, it moves from it to the adjacent bond and forms a pi bond. So here you see a lone pair of electrons on Y shifts to the bond next to it, and this now becomes a double bond. Or a double bond means the first one was obviously the sigma bond. The second bond that is formed is a pi bond. So we'll say it moves, a pair of electrons is moving from the atom to the adjacent bond position, making it a double bond. So we saw that the movement of electrons can take place in single steps, and these steps are shown by arrows and curved arrows which show the movement. The second way how we show the electron movement, now this is when the electrons are moving as a pair. But if electrons are moving single, one electron is going in one direction, the other is going in the other direction, as is done in the case of formation of free radicals. So in that case we use a single barbed fish hook arrow. We call it a single barbed fish hook arrow. This is a single curved, and it is a fish hook, like a fish hook that you put inside for the fishermen put in to catch fish. That it's a single hook. It's not a double hook like this. So it has a single barb, and it's a fish hook arrow notation. The single barbed fish hook arrow notation is used to show the movement of a single electron from an electron pair. The electron pair may be from a lone pair or it may be from a bond pair, but it is a single electron which is moving. So single barbed fish hook arrow shows the movement of single electrons. Now an example is given here, an example of both the double electron movement and single electron movement. The first is a double electron movement. For example, you have the transfer of OH negative giving ethanol. Here you have OH negative ion, and in OH negative ion, one of the pairs of electron, the lone pairs on oxygen, it goes to CH3. And this bond, the electrons of this bond move towards Br. So Br, which had 6 electrons plus 1, 7 electrons, the 7th electron was forming a bond with the carbon. Both of these electrons move to Br, giving back bromine's electron, that is now bromine gets back its 7 electrons, valence electrons, and 1 electron of carbon, thereby turning bromine into a bromide ion. So it will turn into Br negative. 7 electrons were of bromine and 1 electron was from this bond which actually belonged to carbon. So this bond pair has been moved towards bromine, thereby giving it 4 lone pairs, and it results in the formation of the bromide ion. At the same time, 1 lone pair from OH negative comes here, and as soon as this 1 lone pair moves from OH negative to form a bond here, the negative charge will be lost. So it will result in the formation of methanol. So in this reaction, using the curved arrow notation, we have shown where the electrons move, so which bond broke and how was the bond formed, new bond formed. The other example here is the dissociation of chloromethane. In the case of the dissociation of chloromethane, we notice that 2 free radicals are formed. Chloromethane is CH3Cl. So this is the methyl and the chlorine. the bond between carbon and chlorine breaks. And this is what kind of a fission would result in this? What kind of fission is this? This is homolytic fission, where the breaking of the bond is taking place in such a way that both the atoms get back their electrons. So the carbon gets back its electron, and therefore now, since its octet is not complete, it has a single electron, unpaired electron. So it results in the formation of a methyl free radical, and chlorine gets back its electron and it now has 7 electrons. So it is chlorine free radical. Free radicals, like ions, are very unstable. They are just an intermediate. They will definitely react and complete their octet, but this is an intermediate stage which is formed. So this was about the electron movement in organic reactions, how we show the movement of electrons in organic when we are writing down organic reactions. Now come to the second part, the second subtopic. Electron displacement effects in covalent bonds. When electrons displace, how does it affect the molecule? Whenever you have covalent bonds and electrons, a covalent bond is formed by the sharing of one electron each. That is, sharing a pair of electrons between two atoms. And if these electrons move, it results in the movement of negative charge, which leads to a polarity in the molecule. It leads to a kind of a polarity. Now this polarity may be caused in two ways. Either the polarity is due to a species or an atom or a group which is present within the molecule, which is causing the shift due to the difference in electronegativity. It has a tendency to pull electrons towards itself, or it has a tendency to push away electrons from itself. So either this movement of electrons is taking place due to some species which is present inside the molecule, or there is a possibility that the electrons are getting displaced as a result of an attacking reagent. The attacking reagent is such that has a tendency to either push electrons or pull electrons. Therefore, the molecule or the bonds in the presence, or the electrons in the presence of that attacking reagent, will either get attracted to it or get repelled from it. If they get attracted towards it, the remaining part becomes positive. If they get repelled from it, the remaining part becomes negative. So a polarity in any case is created. So whether the species is present inside the molecule, or this polarity is created as a result of an attacking agent, there is always an effect of this electron displacement on the covalent bonds. It would lead to polarity. Now, if the change or the polarity is being created within the molecule itself has a species or an atom which is electronegative or electropositive, then the polarity that it will create in the molecule will be permanent. It will be a permanent effect, that it is present in the molecule. So it is as if, having something, let us say, having a magnet inside a box of nails. So if you have the magnet inside the box of nails, it's going to permanently keep all the nails stuck to it, because it's going to be a permanent effect. It is there in the box. But if a magnet, let us say there's a box of nails that you have, and you slowly slide a magnet beside it, it is just passing by the magnet, you will see all the nails going to one side and then moving along in the box. On the wall, you will see all the nails aligning themselves along with the movement of the magnet, and the magnet leaves. So it was not a permanent effect. The attraction was only temporary for as long as that species was moving next to it. Right? So in the same way, when these electron displacements, if the cause of the displacement is within the molecule, then it is a permanent effect. But if the cause of this displacement is not within the molecule, it is that of an attacking agent, then it is a temporary effect. So let us just study about it. Electron displacement may occur in the ground state or under the influence of a reagent. When we say in the ground state, it means the molecule itself has something which is already causing polarity in it. That is, the cause of polarity is within the molecule. or it may be under the influence of a reagent. That would be a temporary effect. But if it is in the ground state, then it is a permanent effect. The electron displacement due to the influence of an atom or a substituent which is present inside the molecule would cause a permanent polarization of the bond. Let us say that you have in the molecule, you have an oxygen atom. That oxygen is more electronegative than any carbon in the molecule. So it is definitely going to attract electrons towards itself, thereby making the adjacent atom partially positive. So it is definitely going to have a polarizing effect, and this effect will be permanent because that oxygen is always going to stay in the molecule. So if the substituent or the atom is present in the molecule, it will cause a permanent polarization of the bond. Examples of these effects are two. One is inductive effect and the other is resonance effect. Now I'll only use these names right now because in the subsequent videos we are going to do these one by one. So for you right now, you only need to remember this, that inductive effect and resonance effects are permanent effects. They are caused as a result of an atom or a species, a substituent which is present within the molecule, right? And these are permanent electron displacements. So these are permanent electron displacements, therefore they cause permanent polarization of the bond. The second possibility is of a temporary electron displacement. But temporary electron displacement effects, when are they seen? When the magnet is moving outside, it is coming closer, or it is moving away. So it's a temporary effect. Temporary electron displacement effects are seen in a molecule when a reagent is approaching to attack it. When it is coming closer and the atoms, the nails, they start behaving differently, right? So these are seen in a molecule when a reagent approaches to attack it. Example of this is electromeric effect. It is also known as the polarizability effect. So these effects we'll be studying in the consecutive videos. Right now you just need to remember what? That inductive effect and resonance effects are permanent effects, and electromeric effect or polarizability effect is a temporary effect. Permanent effects are caused due to species that are present within the molecule, and temporary effects are caused due to species that are attacking agents. That is, that are not present within the molecule, they are outside agents, right? So I hope this clarifies these two basic concepts, and with this I'll wrap up today's video. If you found it helpful, give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.